Hey, we have here today an interesting problem from the UNSW Integration Bee 2022. This was knockout round 1, problem 5. We have the integral from 0 to 1 of 2 to the floor log base 2 of x dx. Okay, and you'll notice I already have my graph over here on the right, and that's because we're dealing with the floor function, and it's usually going to be pretty helpful for us to sketch it out and see what's going on. So what I've done is I've just graphed our log base 2 of x, and I've plotted a few specific points, like noticing that the log base 2 of 1 here is going to be 0, and then when our x value is 1/2, we get -1. When x is a quarter, we get -2. When x is an eighth, we get a -3. And this would keep going, right? I just didn't have enough space to write it. So like at 1/16, it's going to be -4. At 1/32, it's going to be -5, etc. So we have this graph of log base 2 of x, but what we really want is the graph of the floor function. But we can draw that pretty easily just looking at it in pieces. So what the floor function is going to do in this graph is it's going to round us down to the next highest integer in any region. So like, for example, just looking between 1/2 and 1, the point at 1 where it's actually 0 is negligible, but everything else here from 1/2 to 1, this is going to get rounded down. All these points here are going to get rounded down to -1. And then we can do the exact same thing from a quarter to 1/2. All these points in here between -1 and -2, they all get rounded down to -2. And then between an eighth and a fourth, everything's going to get rounded down to -3 in this region, but you're going to have a bunch of decimals between -2 and -3. But this is going to keep going, and it's going to get like infinitely close to this y-axis as this trails off to -infinity. But what this graph does is it's going to allow us to know exactly what the value of this function is going to be within these different regions, so we can just break up our integral based on these points that we found. So for example, we know what this exponent value is going to be between 1/2 and 1. It's going to be this constant value, -1, and then in this region it's going to be -2. So that's going to allow me to break up my integral. So what I'll do for my bounds is, like for this first one, we'll integrate from 1/2 to 1. We'll have our base 2 here, but we know that this exponent in that whole region is going to be -1. And so we're just integrating 2 to the -1. And then we can do the same thing in this region from 1/4 to 1/2. Everything here is going to be -2, so we're integrating 2 to the -2. And then between 1/8 and a fourth, we can integrate this one, and everything's going to be at -3, so we're integrating 2 to the -3 dx. And of course, this is going to go on forever. This is never going to get completely to 0. We're just going to get closer and closer to 0. So now I can basically just integrate this infinitely many times. Now, so for 2 to the -1, I'm going to write this as 1/2, and integrating 1/2, we're just going to get 1/2 times x, and we're just going to need to evaluate that. And then the same thing here, 2 to the -2, that's actually 1/4. And so we integrate that, and we're going to need to evaluate. And then we're going to have 1/8 times x, and this is going to go on and on forever. But then we can just evaluate this. We just need to plug in all of our endpoints into this thing. And then when we simplify this, you'll notice this here is just 1/2. This here is just 1/4. This here is just 1/8. And so after simplifying everything, we have 1/2 squared plus 1/4 squared plus 1/8 squared plus 1/16 squared, on and on and on. And it might actually be a little nicer if we just square everything out and see this is actually just 1/4 plus 1/16 plus 1/64 plus 1/256. And what you notice from here is this is actually a geometric series, so we can actually just calculate this and finish it off. But let's look at our formula for the geometric series real quick. So for the geometric series, what it really means is to go from one term to the next term in our series, we're just multiplying by a common ratio. So in this case, it's 1/4. Notice 1/4 times 1/4 gets us to 1/16. And then doing it again, multiplying by 1/4 times 1/16 gets us to 64. And then again and on forever, we're just multiplying by 1/4. So in this formula over here, the common ratio is going to be 1/4. And for this to converge, we have this condition here that the absolute value of r has to be less than 1, but 1/4 is less than 1, so we're good on this condition, so we don't have to worry about that. And then in this formula, this a value is just our first term. We can just use this 1/4 here. So r is 1/4, but a is also going to be 1/4. And because we have our a and r value, it's going to be very easy to calculate this, so we can just plug this in. So in our numerator, our a value is going to be 1/4, and then we're just going to have 1 minus 1/4. Well, that's just going to give us 1/4 over 3/4. And dividing 1/4 by 3/4, we just get our final solution, which is just going to be 1/3. So that's it. Thought it was a pretty good problem, so we'll stop it there. Thanks everyone for watching today. Have a great day.